Hey everyone, and welcome to this explainer. I am absolutely thrilled to dive into this with you today, because honestly, we are looking at something that is fundamentally changing the landscape of human knowledge. We're talking about mathematics, and specifically how artificial intelligence is shifting the entire field from an era of proof scarcity to an era of proof abundance. It's a massive, massive transformation, and it requires a completely new way of thinking if we actually want to manage it.
So, here's our roadmap for today. We'll start by looking at this shift from scarcity to abundance, dive into what's called the proof digestion bottleneck, and then examine the mathematical incentive gap. After that, we'll explore this really cool concept of highways versus pedestrian streets, walk through the energetic paradigm workflow, and finally arrive at the ultimate talk test. All right, part 1. From scarcity to abundance. Let's see exactly how AI flipped the script.
Think about how math has worked for literally centuries. It operated under a condition of absolute scarcity. Producing a valid proof was a grueling, hard problem. It required rare insight, decades of sustained human effort, and this incredibly long search just to produce one precious proof. Major conjectures would sit unresolved for generations. But today, AI, automated theorem provers, systems like Lean, they are completely changing the game. We're moving away from that long search into an era of massive generation. Candidate arguments are generated at lightning speed, correctness can often be checked automatically, and this leads directly to, well, congestion.
And that brings us to the core thesis of our explainer today, because having AI generate proofs doesn't actually complete mathematics. The constraint hasn't disappeared, it's just shifted. You see, a proof is not fully valuable just because an AI says it's correct. The new bottleneck is proof digestion. For a proof to be truly useful to humanity, it has to be understood, simplified, connected to prior work, explained, taught, and reused. Correctness is literally just the starting line.
Which leads us perfectly into part 2, the proof digestion bottleneck, and why correctness is absolutely not the same thing as understanding. Mathematical work really builds through 3 distinct stages. Now, AI is becoming incredibly strong at stage 1, generating proofs, and stage 2, verifying those proofs. But stage 3, proof digestion, that is where the whole system chokes. A perfectly valid proof, verified by an AI, can still look like unreadable, mathematically unhealthy spaghetti code to a human. This is where a system called the energetic paradigm, or EP, steps in. EP governs the full flow from a problem to actual knowledge using several levels of control. It uses validity control to ensure correctness, context control to prevent misinterpretation, incentive control to balance academic rewards, tool control to guide AI behavior, educational control to preserve learning, and infrastructure control to smartly allocate automation.
To really get why AI struggles so much with digestion, we have to distinguish between explicit and hidden goals. When you ask an AI for a proof, its explicit goal is just prove the theorem. Done. But humans working on a problem, we naturally achieve all these crucial hidden goals along the way. We build intuition, we figure out methods, we connect our work to older literature, we preserve the paths that failed so others don't repeat them, we create reusable concepts, and we train junior researchers. AI just skips all of that. So the energetic paradigm says we have to make these hidden goals explicit. Under EP, a good proof request actually demands assumptions, dependencies, bottlenecks, failed attempts, and simplifications right alongside the final answer.
All right, part 3, the mathematical incentive gap. Let's talk about why this giant warehouse of proofs just keeps growing.
Here's the harsh reality of academia. The current reward system heavily favors first proofs. Discovering something first brings headlines, it brings promotion, it brings the funding. Meanwhile, the later work, the work that actually solves that digestion bottleneck we talked about, gets very little recognition. If we want to fix this, we need real reforms. We have to start rewarding proof simplification. We need to reward the people building formal libraries, reward exposition, reward the archiving of failures, and genuinely recognize dedicated digestion teams.
Because AI is cranking out so many correct but completely undigested proofs, we are facing intense knowledge congestion. It's basically a massive overflowing warehouse filled with correct proofs that do not translate into actual progress. In EP terms, mathematical energy is flowing entirely toward production, while digestion is completely starved.
Moving on to part 4, highways and pedestrian streets. This is all about routing that mathematical energy.
I absolutely love the transportation analogy the energetic paradigm uses here to govern how we allocate automation.
Imagine mathematical highways. These are for tasks where raw speed is your best friend, things like routine checking, heavy computation, and formal expansion. These are perfectly suited for AI automation. But we also desperately need mathematical pedestrian streets. These are spaces for the slow conceptual work, for synthesis, teaching, and evaluation. That requires slower, deliberate human reasoning. EP carefully determines where speed actually helps and where it just harms the process. So, we need a strict, really functional division of labor based on actual strengths. AI is incredibly powerful at generating options, searching paths, checking consistency at scale, and organizing information. Humans, under the EP framework, are responsible for judging meaning, identifying the key ideas, evaluating what's actually important, and keeping the whole system coherent. The goal here is a clean, functional allocation of tasks. Let's look at Part 5, the energetic paradigm workflow, building a system for truly durable knowledge.
Now you might be sitting there wondering, why can't we just score an AI on how well it digests information? Well, simply put, AI models are really good at faking it. They can imitate understanding perfectly. This leads to reward hacking. The AI might add a bunch of irrelevant citations to look smart, label totally routine steps as novel, or spit out polished explanations that are incredibly shallow. A simple score just cannot replace real human digestion.
So to stop this reward hacking and build genuine understanding, EP uses a comprehensive 10-step workflow. It starts with problem intake to define goals, moves to structure mapping to find related work, and uses search routing to divide the automated and human tasks. Then AI generates the proof, and verification checks the correctness. But then comes the human element. Digestion to simplify ideas, the talk test to ensure real understanding, education transfer to make it teachable, failure memory to save unsuccessful paths, and infrastructure updates to organize it all. It governs the full chain of production. The big takeaway here? Formal proof verification tools are absolutely necessary, for sure, but they are only the gate of correctness. Correctness is a gate you have to pass through, but it is not the entire road to mathematical progress.
Which brings us to our final section, Part 6, the ultimate talk test, the final human gate.
Step 7 of that workflow we just looked at is the climax of human verification. Under the talk test, a mathematical problem is not considered fully solved until a qualified human can stand up in front of their peers, explain the proof clearly, answer adversarial questions from experts, connect it to existing literature, and defend why it actually matters. It demands true narrative clarity and prove that it can be taught downstream. To actually pass this talk test in a world flooded with AI, our education systems are going to have to evolve big time. We need to shift from just getting the final answer to training students in human judgment. They need to learn how to decompose problems for AI, how to prompt models without surrendering their own mathematical responsibility, how to detect that fake elegance we talked about, and ultimately how to convert raw formal machine output into a compelling human explanation.
So what does this all boil down to? It's this critical realization. AI creates proof abundance, yes, but abundance is not progress. Without digestion, mathematics is just going to accumulate correct but entirely unusable results. The energetic paradigm turns proof production into a system for durable knowledge. It demands that we invest heavily in the human systems required to actually absorb what AI produces.
I want to leave you with a final, slightly provocative thought about the future of human understanding in an automated world. Think about this. If an AI generates a proof and no qualified human can explain it, defend it, teach it, or use it, has the field actually received it? It's a fascinating question, and honestly, the answer is going to define the next century of research. Thank you so much for joining me on this explainer today, and I highly encourage you to keep questioning what true understanding really means.